Everybody, welcome to our weekly talk on computer system. One of the things that I've remembered for many years is the difficulty of programming concurrency. And of course, now that all of our machines are multi-core machines, concurrency lives on every application that we encounter. So I think that today's talk is particularly timely because it has to do with programming and correctness with threads. And our speaker is Caitlin Sadowski, who is finishing up her PhD at the University of California, Santa Cruz. So she's come over the hill today to give us a talk. Caitlin?
Hello. Strange echo. Okay. So my name is Caitlin, and I'm a PhD candidate at the University of California at Santa Cruz, where I work on a variety of projects, but many of them are related to parallel programming. So today I'm going to start out by talking about my background and sort of parallel computing in general, and I'm going to tell you about a couple interesting correctness conditions for concurrency that you may or may not have heard of. One in particular that I've done a lot of recent work on, and I'll talk about how you can use dynamic analysis to check for that correctness condition. Okay, so kind of the key thing that I'm interested in as a researcher is helping and understanding developers and to a lesser extent researchers. So this means things like developing tool support, program analysis tools, tools to find bugs in programs, things like that. Also development of novel user evaluation techniques and incorporating user evaluation techniques. Empirical results, so things like looking at developer artifacts to find out about behaviors, and also developing educational materials. So this is kind of my past research in a Venn diagram form. So the two biggest areas that I've worked in are parallel computing and empirical software engineering. I've briefly mentioned the empirical software engineering work, both user evaluations and studying developer artifacts. I'm not really going to talk about this today, unfortunately, but if any of you are interested, feel free to talk to me afterwards or email me to ask further. So I have a lot of work on parallel computation, specifically. As you can see, I've got some sort of performance focus. So this includes scheduling algorithms that can make stuff more efficient, a new model for parallel computation, some education materials, and then also most of the work that I've done and that is going into my thesis is focused on correctness. So static analysis and dynamic analysis, so analyzing the source code or a running program. And today I'm going to talk about dynamic analysis, which you can see I have several papers in. And specifically, I'm going to talk about this one particular area that I'm interested in, cooperability. And I think I'm not going to have time to talk too much about deterministic parallelism, but if you're interested in that, we can chat more later. The other thing about myself that is important to know is that I love to collaborate. So far I've worked with about 27 researchers at 10 different institutions in a few different countries. And I intend to continue these collaborations into the future. Okay, so let's talk about parallel computing for a little bit. So probably all of you are familiar with what parallel computing is, at least in a high-level sense. You've heard buzzwords lately, increasing numbers of buzzwords. This is like the obligatory graph in any talk about parallel computing. So how many of you guys have seen this graph before? Yeah, so what this is, we have speed, processor speed over time. And it used to be that processor speeds were increasing pretty steadily up until about 2005 and 2006. Moore's law still holds, but we hit a power wall. And so now it's not energy efficient. It doesn't make sense energy-wise to actually have a single core computer anymore. And all the major chip manufacturers have switched to multi-core. So you see this in iPhones, you see this in embedded devices and in personal computers. So it's no longer the future, it's actually the present. And the question I always get is, do developers, all right, so we know that the hardware's changed, and since there's been a big change in hardware, that means there's going to be some changes in software, but how many developers does this affect? Do developers really use concurrency? So I only know of one survey that looked at this. If any of you know of more, please let me know. This is looking at concurrency at Microsoft. They surveyed about 700 developers. I think they had a sample size of maybe like 3,000 randomly selected developers, and here's who responded to the survey. And they asked about how these developers use concurrency in their day-to-day work at Microsoft. They found 66% of developers have to interact with concurrency. So they were surprised. This is most developers. Interact is really big. So 10% of developers have to either detect, debug, or fix a concurrency bug at least once a week. So 10% may not seem super big. About 30%, so about half of this number, had to detect a bug or fix a concurrency bug at least once a month, which is still pretty substantial. And the thing about this 10% is that concurrency is particularly difficult. So they also found that most developers perceive concurrency bugs as severe and really hard to reproduce. And in fact, okay. And in fact, you see that concurrency is hard. This idea is reproduced many places. This is a quote from some interviews that I've been running with developers in the Silicon Valley area about how they use program analysis tools and other methods to find errors in concurrent code. So we still get race conditions getting into production and crashing things. So this is a source of bugs that are pretty severe. Crashing production systems is pretty bad. And also, in this talk, I'm going to focus on multi-threading, which is also particularly difficult. I don't know if you guys have ever read any of these papers, but Edward E. Lee has a paper, The Problem with Threads, is really interesting to read about how threads are difficult to reason about. So here's kind of, in a nutshell, what is so difficult. So what is the semantics of X++? So you guys have seen X++ before. It's in many different languages. It's pretty common.
Add one to itself. Right. Yeah. Increment your variable.
Yeah. So in sequential semantics, it's just a simple increment, right? You're just adding one. But X++, even though it looks like one programming statement, what is it doing? Well, you have to read in the value of X, you have to modify it, and then you have to write it again. So when you have multi-threaded semantics, all of a sudden, you have a potentially non-atomic read, modify, write sequence, even though it just looks like one statement in the program. So you have to worry about, during this X++ computation, some other thread might come in and do something funny with X. There could be a context switch. The thread could interfere. This is really difficult to reason about. Even things that look from the programming languages level like a single statement, they're actually broken up into these complicated blocks with thread interference at any point. The other thing I want to mention is that concurrency errors are not just at one point in time. So this graph is from a project that I've been working on looking at concurrency errors over time. So what these are all variables that race in JEdit, which is like a editing program. And these are sampled revision numbers. So like this line here is saying that this particular variable was racy for all of these revisions. So this is, a lot of stuff in the graph. The two things I want you to notice are, one, that these errors persist. So there's a lot of racy variables that are racy for a long time. And also that here there's at least one place, I'm seeing this other places, where a variable stops being racy but then comes back and is racy again later. So, these are races. Maybe some of these are benign. There's actually debate whether benign race makes sense or not. There's a paper called Data races are evil with no exceptions. That's an interesting position paper on that. The other thing, though, is there's a paper from FSC this year that found that 40% of concurrency bugs that are fixed, so if these bugs are fixed, that means that someone cared enough to go about fixing them, in operating systems were actually fixed incorrectly. So this is pretty big number of bugs fixed incorrectly. So, all right, so we've talked about that, concurrency is really important now. Concurrency bugs are pretty prevalent. So, but what does correctness mean for multi-threaded programs? I mean, you have general program correctness. You have tests you want to pass or fail or whatever. But what are some specific properties for multi-threaded programs? I mean, you guys have all heard of some of these. The deadly embrace, which is the original name for deadlocks. Do any others pop to mind?
Live lock.
Live lock.
Thundering herd problem.
So most of them so depending on how you define these, the deadlock freedom, no ordering violations. This is actually interesting because there's been less work on it. This is like one thread is responsible for initializing a data structure and other threads use that. Well, that data structure better have been initialized before it was used. But you might have implicit ordering constraints that the program does not obey. Data race freedom, this is another big one. And atomicity violations, which if you're not familiar with, we're going to talk more about them. There is a paper from 2008 that was looking at, I believe, Firefox mostly, and they found that 97% of concurrency bugs fit into one of these categories. And so a really big class of them are atomicity violations. So have you guys heard of atomicity before as a property? It's definitely a property in databases. Let's talk about it for a little bit. So here, all right, so in order to talk about atomicity in the context of multi-threaded programs, I'm going to unroll a little and talk about race conditions, because basically atomicity generalizes the concept of a race condition. So what's a race? We have two concurrent unsynchronized accesses to the same shared variable, at least one of which is a write. So over here I've got two threads, thread A and thread B, and thread A is reading from balance and then writing to balance. So maybe this is a bank account, and basically I'm adding $10 to my bank account. This thread, I'm subtracting $10 to my bank account. So if I add $10 and then subtract $10, I should end up with what I started with, not some funny other value. So over here, like this is sort of the implicit assumption for how stuff is going to execute. One thread is going to do its business, and another thread is going to do its business, and we end up with the same value. But of course, in multi-threaded programming, we have this preemptive semantics. A preemption could happen at any point. Some other thread could be scheduled. You have to worry about a situation like this. So I've got two threads. They each read balance. So let's say balance starts as 0. So they both read 0. This one then writes 10, and then this one writes -10. So instead of 0, we ended up with -10. Okay, so how do you fix data races? Well, the key here is that it's unsynchronized. So the way to deal with something that's unsynchronized is to add locks. All right, so here's the problem. If you add locks, that's great. We now protect every access to balance with a lock. There's no I think so. Yeah. Yeah, I'm not sure where it's coming from.
Could be the mic on your Mac. Could be the mic on your Mac.
Yeah, but
Yeah,
I'm not sure why it would be
I
on.
think he turned it off. Ron, you turned it off, right?
All right, let's go.
Anyway.
All right. I could turn this one off if it's distracting and go stand over there. Okay. Okay, so the point here is that we have protected access. Every access to balance is protected by lock M. So there's no sort of data races at the most basic definition here. But The issue is that wasn't really the developer intent. Like, you can all look at this and see that something is wrong. These operations were supposed to be grouped together. When I was reading the balance and then writing it, that was forming one group, and now we've lost that cohesion. So that's kind of what atomicity is about, is you have this cohesive section of operations. On a side note, race freedom is really important for some languages, because in Java, for example, a right to a long might not be atomic. So you could actually end up with garbage values if you have two unprotected rights to a long. Okay. So the key idea is that when you have an atomic method, it has to behave as if it's executed serially, so as if it's executed without any interleaved operations by other threads. So normally when you have some kind of code and it's multi-threaded, at every program point you need to think about, is there thread interference I need to worry about? Is there thread interference I need to worry about? So if you have an atomic method, if you know it's atomic, you know you don't have to worry about that. So the big benefit is that you can use sequential reasoning, which everyone tends to be more familiar with because this is what you're taught from the first programming class that you encounter. And these atomic blocks are going to execute as if they're free from any interference. Okay, so that is sort of atomicity in a nutshell, which brings me to the property that I've worked a lot more on, which is called cooperability. So let's go back here. What's the semantics of X++? So there's a difference between single-threaded and multi-threaded, but also if we have an atomic section with X++ in it, it's an increment, right? Atomic means everything in there is grouped together, either through analysis or through some kind of programming model. We have a guarantee of that. Doesn't matter how we got the guarantee, but if I have an atomic X++, I know it's an increment. But I still have these other sections in my code that are not atomic, and now we're back to the old difficulty where I have a potentially non-atomic read, modify, write sequence. So the big problem here is that I have a bimodal semantics. You have to think about, is this code inside of an atomic block or not? And if it's not, you have to reason about it differently than if it is. And actually, I don't know how familiar any of you are with transactional memory, but this is a big problem with software transactional memory systems, is that the idea was it would be easier to reason about, but it's not, because of this bimodal semantics. Is a big issue in reasoning about it. You have to reason about whether your code's in or outside a transaction. All right. So instead, there's sort of a new methodology for thinking about thread interference. You want to make thread interference explicit by having yield points in your code. So these are the points where thread interference matters, basically. Where if a context switch occurred, behavior could change only at these points. And now sequential reasoning is going to be correct by default because you know exactly which program points between two operations you need to worry about. So there's kind of two hypotheses with this methodology. That there's less program points to reason about now because we only have specific yield points in our code, and that having these yield points, these points that are of thread interference, will actually help people when they're debugging and understanding code. So now we have yield annotations before and after. So all of a sudden, so this may seem like a relatively simple shift, but it actually sort of affects your whole mindset with how you think about thread interference. So now there's cooperative semantics. So X++ is always going to be a simple increment because otherwise it would have to be some kind of t equals x yield x gets t plus 1. So whenever you see X++, you know that you don't have to worry about thread interference because the interference is only yield annotation.
So how is this different? I mean, we've had semaphores and other kind of ways of locking things all along. You know, I mean, this is kind of a normal thing that you gotta not do something while somebody else is
totally
doing something.
orthogonal from locking. So you have your program, you have your locking discipline, you have your concurrent code, and now you have to think about it. So you have to think about what what does correctness mean? So like this is sort of like, what is the specification for my code for how threads can interfere with my code in a way that I know about or in a way that I don't know about. So like an unexpected yield would be a way that I didn't know about.
I don't understand how it's orthogonal, but I don't want to stop you.
Okay.
So is this the equivalent of cooperative multitasking? Is that what this is?
No. So I think that's actually the next slide.
Oh, I have a question on that last one though. So have you looked at the IBM RP3 architecture and the NYU Ultra Computer?
No, not too much.
I would recommend looking at those.
Okay.
People too.
So there's a big distinction in terms of, so there's many ways to go about sort of in general correctness and multi-threaded programs. There's sort of two big things we could do. There's analysis and there's enforcement. So we have this idea that given a program, we want to make the interference explicit with yield points. So we could either develop an analysis tool that you put in as so basically the analysis tool, you feed into it your program with locks and whatever else, and you feed into it a bunch of yield annotations. And the analysis will say, yes, this completely summarizes the thread interference in your program, or no, it doesn't. The other way, this is the cooperative multi-threading way, is you could actually have a scheduler that changes the behavior of the program and ensures that you only context switch at yield points, or else the behavior is equivalent to a program that does that. So here I'm going to talk about analysis. So what is the big trade-off here? So analysis allows you to add in this kind of specification without changing runtime behavior for your program. So you now have a reasoning edge where you can do sequential reasoning, but the performance is the same.
Does this deny the ability to do like a preemptive multitask activity because it's outside of the yield point though at runtime?
So at runtime, you schedule your program like normal. You don't have to worry about the yield points at runtime. So the yield points are something that you check through your testing phase. So you could do static analysis. We have a static analysis tool and a dynamic analysis tool. So you go through like a pre-phase basically where you think about the yields in your program, you see if those yields make sense to you, and then at runtime you're just running a multi-threaded program like normal.
I'm sorry, this is a good time to ask the question, but I'm wondering, does this mean that a multi-threaded preemptive multi-threaded OS would not do a context switch for your program outside of its yield points?
No. The operating system behaves just like normal. So this is totally in the analysis realm. So you could write a scheduler that only did switching at yield points, but that would have performance impacts on the program.
So without that, though, how do you safeguard the analysis that says that it would be great if the yield points were here, but if it's not enforced, then how do you make sure it works?
So the analysis is to check your impression of where the yield points are. So the idea is like the yield points are there for developers to understand their code better.
Okay.
They're there for you to write a specification into the code and then check that specification. And they're there for future people that work on the program, so they can say, okay, these are the points where the previous developer intended there to be interference. So there's a split between intended and unintended interference. So sometimes like you need to switch threads. It's okay. And other times like, well, you kind of didn't mean to switch threads in there. That's why you were protecting it with locks, but you forgot and used two different locks or something. So I guess the idea here is that a lot of these different kinds of errors, so atomicity violations, data races, and to a lesser extent deadlocks, they kind of come down to an unintended point of thread interference. That's sort of like what caused the error. So if you could document the points of thread interference and check them, then you're closer to understanding why there's the error. Okay, so we end up with this. There's a methodology of developing multi-threaded programs. So the first thing is you have a program, it has yield points, and those yield points represent all the places where thread interference matters in your program. So in that case, we say that it's cooperable. That's where cooperability comes from. And it comes from cooperative scheduling. That's where we're using these words. So how do you check that all the yield points are represented? This is where tooling comes in. So I'm going to talk about copper and silver, which is a dynamic yield checker and yield inferencer today. So you check the yield points with tooling, and then you reason about your program. But now when you reason about your program, you can just think as if the context switches were at yield points. So when you're reasoning, you can leverage those yield points to make it easier to think about the program. So that's sort of the idea behind this. So this cooperative scheduling, correct under cooperative scheduling is where you actually do switch at yield points. So the yield points are exhaustive. If those yield points were actually, if we're running under a cooperative scheduler, it would be correct. And this is the part where the programmer has to think about. You have to reason about the yields in your program. And from these two, you get a guarantee that it's going to be correct when you just run it on your multi-threaded hardware. So it's basically a new way of thinking about multi-threaded programming and a new way of sort of understanding multi-threaded programs.
So doesn't that mean the programmer has to know more about the implementation of the programming language? Because you have to know, for example, that X++ is potentially non-atomic
Yes.
as a programmer to reason about it.
Yes. So I would say if you're writing multi-threaded code, you usually have to know about the implementation in order, because there's all these challenges. So this gives you something to leverage to help document that knowledge for someone else, and to also help focus your reasoning in terms of interference points.
You're using the term reasoning several
Yeah.
times, and also analysis. I'm trying to figure out if these are ad hoc things, or these you have some production system approach, or what you mean by. It probably will come out in your talk.
Okay.
But I don't. Is this a formal reasoning or a formal analysis, or is this somebody going, "Gosh, I bet you there's a yield needed here"?
This is actually tooling, so program analysis tools. There's existing tools for analyzing Java programs that I wrote, and there are hopefully soon going to be tools for C++ tools, for C++, analyzing C++ programs that someone at Google is writing.
Okay, and there's some sense of semantics, and there's some sense of
There is a proof of correctness. There's a formalism in the paper you can read if you want. There's all that good stuff too. I'm not going to go into any of that today.
Okay, good.
If you're curious about how the proof is structured or how the formalism works, you can ask me about it. In terms of the reasoning part, this is a little bit more fluffy, and one challenge is how do you evaluate that kind of, mostly when people make tools, they want them to help developers that are using these tools. But how do you evaluate that? How do you evaluate that this makes it easier to reason about multi-threaded programs? I'll talk about that a little more.
For the programmer to think about it.
Yeah. In fact, I'll talk about that right now. So, I mentioned that I work on some more empirical software engineering stuff. One paper that I had recently was on looking at how researchers use user evaluations in software engineering papers. So we looked at a whole bunch of software engineering papers in the past 10 years of this assortment of conferences, and found a variety of things, including user evaluations are on the rise. So when I was preparing this talk, I looked up papers that are about concurrency at these conferences in the past 10 years, and how many of them do some sort of user evaluation. And the answer was 2%, which is really low. It's a lot lower than it was in general. So, and a big challenge is, so we wanted to do an evaluation of this idea that cooperability could help people reason about their programs. Now, to some degree, the best evaluation is going to be actually people in industry using it. But we wanted to sort of initially like evaluate something small, look at whether this was helpful at all. So I did a user evaluation focused on mostly this hypothesis that if you gave a programmer code with yields in it and it had a bug, they would be able to find the bug, maybe easier than without yields. So this is like a very sort of simple hypothesis along the range of many things that we think yields could help with. So there's a couple other ones that we looked at in this study. So the second was that maybe participants would have a higher subjective impression of code with yield annotations. Maybe they would think they could understand the code better. And the third was we thought maybe, well, if you're an expert, if you say that you've had many years programming with multi-threading and you would rate yourself as an expert, then maybe you would have an easier time finding bugs. So the results were that there was a statistically significant difference. Participants had an easier time finding bugs in code that was annotated correctly with yield annotations. There was no difference in terms of subjective impressions, or the difference was not statistically significant, rather. And there was also no statistically significant difference for expert participants. So this is something you see a lot, that subjective impressions are not necessarily correlated with what people do. And also that if you ask people if they're an expert, they might not know. They might not be able to tell you accurately. You really need to think about what an expert means for what you're doing.
People were involved?
Let's see. I think it was about 30 something in this one. I'll show you on the next slide has some numbers. Not this one after. So we decided to use an internet-based survey. So I personally am really into lightweight user evaluation methodologies that you can deploy at multiple locations, that you can look at something very specific and get some feedback quickly. We had a mix of developers and students. I think it was maybe 50-50, people ranging in experience from like 3 years to 30 years. You had to be pretty familiar with multi-threaded programming to read code samples, so we only selected people that had already had some experience. And we presented people with 3 code samples. It was a between group design, so you have with or without yields, and participants had to identify all bugs. Okay, so this is the, so we had 36, so 30 out of 36. This is across all the samples. 30 out of 36 people with yield annotations could correctly identify the concurrency bug versus 21 out of 44 without. So this difference was promising. Of course, as I mentioned, we want to do more. So right now, I'm actually currently working on performing an industrial case study. So some people at Google were interested in using this internally to help people understand code there. And so I have someone there who is working on implementing cooperability checker again in C, C++, and seeing how Google engineers will interact with it. So that's sort of the next step evaluation-wise. Okay, so let's talk a little bit about dynamic analysis. So I've introduced cooperability, which I think is a really cool property. The one thing is it's a little bit complicated to get right away, which is not very good if you want it to be something that helps people understand things, but once people get it, they seem to like it. All right, so concurrency is a problem. You know, how could we address it? This is sort of a map of the related work. So one way you could address it is with a paradigm shift. So you can make up new languages for people to use. And keep in mind that I think you should use all of these together. So there's been a lot of work on kind of embedded domain-specific languages that you can just have one for a little part of your code or for some context. So that's great. but there's also a lot of legacy multi-threaded code that you have to work with, so that's not going to be like the complete solution. Another thing is testing, and there's work on model checking, which is exploring a whole bunch of different thread schedules, or also fuzzing, so exploring maybe like potentially good schedules with heuristics. But a problem here is that when you write your test cases, you're not always thinking about concurrency errors. So you still might need to think about which sections of my code are atomic. That can be hard to write a test case for, but is really easy to write an analysis for. So for analyses, you have sort of static and dynamic, and the trade-off tends to be false positives versus false negatives. So statically, we have all the code, which means that we don't necessarily know exactly what's going to happen at runtime. Dynamically, we don't have all the code. We don't know what unexecuted branches of conditionals, what code could be there. But when you talk to developers, a lack of false positives is really important. So that's one reason why I've done a lot of work in dynamic analysis in specific, which is what I'm going to talk about right now. The other point that I want to make is that developers do use static and dynamic analysis. So I mentioned I'm conducting interviews. I found that in most developers that I've talked to, they're willing to add annotations to multi-threaded code. Not to other code. Not if you said I have this great program analysis technique for some other code. Then they're less excited. But for multi-threaded code, there's a perception that it's so difficult, they're willing to go an extra mile. So as an example, this is a project that I worked on at Google last summer in the Clang C++ compiler. This is a static analysis for verifying thread safety properties. So here you can say that some class is lockable. So here I have a lockable mutex class, and you can explicitly say, all right, this is a lock function, so whenever this function gets called, that means I've acquired a lock on the class. And then later on, you can have a variable and say this variable is guarded by mutex mu. And statically, we'll check and make sure that whenever you access X, you have first called the lock function on mu. So this analysis had previously been implemented in GCC, somewhat working. And so people have actually been using it at Google for the past couple years. And in 1 month, I can't tell you which one, I saw that there were 18 bugs fixed at Google as a direct result of this analysis. So there's actually a large amount of code that's been annotated in this way, and people are willing to do that more. Now, specific teams have a wide range of feelings on whether they're interested in doing this, but it still is pretty popular. And the other reason is that when you talk to people, documentation and program comprehension are the big challenges for concurrency. That developers, you hear them say again and again that they need to understand that code is safe. Not just they want to run tools and be able to check, but they also need to have something in there so they can kind of understand what the tool is doing and why. This is another quote. We wish we had something better, but we don't want less. The problem is just too hard without it. And they're talking about static and dynamic analysis tools. And most people that I talk to actually use both. Dynamic is a bit more popular because of the lack of false positives, but people use, if you have a really nice simple static analysis, like the one I showed you, people will use it. Okay, so let's talk a little bit about the cooperability checker, and then finish up. Okay, so cooperative scheduling, which we talked about before, a cooperative trace, we have a context switch only at yields. Okay, so this is all fine and good, but this is not how programs actually run. This may not be efficient. So instead, when we have a preemptive trace, we're running our program, there could be a context switch anywhere. However, some of these operations do not have any effect if you swap them. So even though this switch has some funny context switches, this trace has some funny context switches, we can actually swap these two operations. This is writing to t, this is writing to x. If I change these operations, the order of these operations, the behavior of the program will not change. So we kind of know if you have two things, they're operating a disjoint data, it doesn't matter, I can reorder them. The same thing if I have a yield and I switch it with this operation by another thread, it doesn't matter. So this trace was equivalent to this cooperative trace. So we say that it's cooperable. This is like the key idea of cooperability. So a program is cooperable if any preemptive trace, so here's our preemptive trace, is going to be equivalent to some cooperative trace. So that was kind of a, so another, you may have seen serializability is another way of doing this. Another phrase that means the same thing. So the operations between yield points form chunks, and those chunks can be serialized into one order. Okay, so that was kind of hand-wavy about what it means for two traces to be equivalent. So many concurrency analyses leverage this thing called the happens before analysis, or the happens before relation, which originally came from Leslie Lamport in a really great paper called Time Clocks and the Ordering of Events in a Distributed System, which if you have not read, I would really recommend it because it's very interesting, and it's also interesting from a philosophical standpoint because he talks about physical time and what it really means, and what time means, and things like that. But the key point is that we don't, if we just use clocks to keep track of things in a distributed system, we have to worry about how different clocks relate. They might not be the same notion of time. So coming out of that is a relation. So this will give us a partial order on traces with a property that if you have two traces with the same partial order, their behavior will be the same. So this is a way that we can check automatically for the same behavior, which is too vague to check otherwise. So you have communication order edges. So if I have a read of a particular variable, the write to that variable happens before the subsequent read. If I have a release of a lock M, that's going to happen before a subsequent acquire. And if I have two operations by the same thread, the first one is going to happen before the second one. And to make this a relation, we're going to combine it with transitivity. So if I have two operations by a thread and the second one happens before this other operation, there's a transitive edge connecting them. Okay, so how does this apply to cooperability? So in the paper that I'm talking about today, we presented two tools. One of them, Copper, detects cooperability violations. So what's a cooperability violation? That will be when a program does not execute as if context switches only occur at yields. So another way to think about this is that there's a missing yield. We're analyzing the trace of the program, and we discover that something funny is going on. It's not the same as if there's context. It's not equivalent in terms of happens before to a trace with context switches only at the yield points. Okay, so we have a transaction between these two yield points, and while we're executing the program, so here we acquire the lock, and then we read X and release the lock, and then we're going to acquire it again, and then we're going to read X and release the lock. So say we have this trace where in between this release and this acquire, another thread comes in and acquires the lock and writes to X and then releases the lock. So now, suddenly, we calculate the happens before between these two transactions. So we see that in any serial trace, so in any trace where the transactions were serialized, there's a happens before edge between this release and this acquire. So this transaction must happen before this transaction in the serializable trace. However, there's also a happens before edge between this release and this acquire. So this transaction must happen before this transaction. So since there's a cycle in the transactional happens before graph, that means there's a missing yield right at the point where we notice the cycle. And so Copper will output an error. You know, there's a missing yield at this line. Maybe you should look at that line and see if that yield was expected and you just didn't realize it, or if there's some kind of bug going on. So silver is kind of a similar idea. We still have a transaction between two yields. We calculate the happens before relation between transactions. But at this point, if we discover a missing yield, we just add it and continue. So we add it to the program. We say, okay, we're going to say there's a yield here, and then we're going to keep executing the analysis tool from that point with the assumption that we had a yield. Okay, so that was a very brief look at two dynamic analysis tools for checking cooperability. There's a lot of implementation challenges in writing these kinds of tools. The biggest thing is scaling to large programs. So there is a lot of, you have to deal with object churn. Basically, when you're writing Java programs, pretty much all of scaling seems to come down to removing unnecessary object allocations. So I can't tell you how many times I've had to write my own garbage collector on top of the Java garbage collector so that I can actually maintain, for example, my own store of nodes and not have any extra nodes allocated. So this was like the big challenge. The analysis does scale up to multi-million line programs like the Eclipse IDE. For our, so for the next question though, running it on programs. So I sort of gave two hypotheses at the beginning of cooperability. One was that these would be easier to reason about. So we looked at that through a user study and now an industrial case study. The other was that there'll be less points to reason about. So kind of a natural question is how much less? Sort of what benefit does this give you in terms of reasoning power? So this is one of the benchmarks we ran it on. This is the Jigsaw web server. And we're looking at three lines, and the thing to notice is that they're like an order of magnitude different. So what are these three lines? So the top one is if you just have to reason about interference in your program, you don't have anything to help you, you need to think about all field accesses and all lock acquires. Because those are the points where you could get funny behavior. Otherwise, we ran an atomicity analysis to identify a set of methods that were atomic. So there's been a lot of research that method level atomicity is pretty good. So when you think about an interface, atomic is pretty good. Because you can say, all right, I know this method's atomic, but when you're down in the code, that's not as helpful. So what if you have atomic methods? So now you have to reason about atomic method calls. Something funny could happen right before you call an atomic method. And when you're not in an atomic method, then you have to reason about the field accesses and lock acquires. And we compare that, to the number of yield points in a program. So if you only specify yield points, it's about 2 orders of magnitude difference in the number of sort of program points where something funny could happen. So it's basically a way to narrow down to the set of program points you really only have to worry about. Okay, so that was a pretty brief tour of one particular research topic I've worked on. So hopefully you got the impression that parallel computing is important, especially right now. There's some really interesting concurrency properties when people think about parallel code. And that one way to address this is through dynamic analysis. And I have actually worked on a variety of dynamic analyses targeted at concurrency properties. I've just told you about one today, but I've worked on a lot, actually, more than I've published. So just to summarize cooperability, so you have explicit discrete thread interleaving points in your program. You have sequential reasoning everywhere because you know exactly the points where you need to think about interference. And the developer will think in terms of transactions, code demarcated by yields at both ends. And sort of, our thesis in this work is that cooperative scheduling is easier to understand, which we're trying to test this hypothesis, and preemptive scheduling will retain the original performance. So that's like the meat of cooperability. All right, so now I'm going to spend a couple minutes talking about the future. Okay, so cooperability. What else would I like to do in there? So I told you that I'm working with some people at Google on an industrial case study. The other thing that I'm interested in is kind of what are the usability trade-offs. So we have atomicity is a pretty good method level specification. So you might say you might use atomic for interfaces, but maybe you want yield points other places in your code. And like, how do yield points relate to ordering constraints? Do you want to have ordering between these yield points? Is that really what's going on when you end up with ordering violations in code? So kind of like, what are the usability trade-offs in these different lightweight annotations for concurrent code? And what kind of annotations are best suited to developer practice? Another thing is, so when we looked at our benchmark suite and all the yield points in the benchmark suite that we ran it on for the paper, we found that these yield points, there's a set of them that were intended. Like, for example, at a barrier call, that's an intended yield. If you're going to have a barrier, you kind of want that context switch to occur, and you want other threads to execute before everybody gets to the barrier, or like at a join point. So there's some points where yields are intended. All the other yield points in the code, it was like all the atomicity violations and race conditions that were in those benchmarks that have been reported by other tools were sort of explained by a yield point. So one thing I want to look more at is how developers reason about concurrency bugs and how that relates to these yield points, how you could leverage it further along in the reasoning process. So there's a difference between sort of a concurrency error and this, this bug in your code. How do you know that this funny behavior is being caused by this particular variable racing? And forming that connection is really difficult. And another thing, is I am planning to move more into sort of distributed systems. So I've been working a lot with multi-threaded computing, but I've been talking to more and more people that have to use distributed systems in their day-to-day jobs in their life and have to reason about it. And in particular, performance is really difficult for distributed systems. So one project that I've been talking about is adding performance assertions. So you could actually say, hey, this part of the code should run faster than this part of the code. Or this should be no more than 5 times slower than this thing over here. Or really, this part of the code is bounded, it's a network is the real bottleneck here. But over here, it's I/O. So this has a lot of applications, both in terms of trying to find performance problems, which is really difficult, and also in terms of optimizing systems that sometimes you need to make these trade-offs, and the programmer is the best place to do it. Another thing, when I talk to people working on distributed systems, pretty much everybody uses logging to find bugs. Logging on a whole bunch of computers at once. Everyone uses logging, but everyone's kind of unhappy with logging. And so there's been different tools, either to help log stuff automatically or analyze logs, but the tools don't really have a lot of traction. So one thing I want to do really soon is an empirical study of how people use logging and really like what are the issues in their logging and where are the points where improvement will really make a difference. Okay, so sort of moving into the future, I've been working on parallel computing and empirical software engineering. I'm excited about continuing more in the intersection of these two. I'm also interested in some more just empirical focused things moving out of parallel computing. But this intersection is really sort of my favorite place to be. All right, that is all that I have to talk about. So feel free to pepper me with questions.
So, a couple. One of them, a lot of application vendors have built platforms, Salesforce.com being a good example of some that runs in the cloud and the databases or who knows where. And people are building thousands of add-on applications to run in an environment in the same way that they build plugins for Eclipse and the like. Is there anything special that you can do to help the developers for something like the Salesforce platform or the Force.com platform to avoid running into these kinds of problems? Or do they need to build stuff into their platform to do the yield checking?
So Salesforce is like like a cloud computing infrastructure, or what?
They offer a customer relationship management system, which is deployed in the cloud, right? No software.
Okay.
They have, in the same way that Google or Amazon, it's all distributed across lots and lots of machines, and people can write add-on applications
So it's like
through a
EC2.
published set of APIs, and so we can take this offline if that's not I thought you might know that as an example. I guess the underlying question is, if people are building to a platform, is the advice, is the direction to instrument and add yield to the platform itself, or do people who are building on top have to do their own work to make this all work out right?
Okay, so I guess if you have a really well-designed platform, then hopefully it will force developers to use good programming patterns and to like hide as much as possible under the rug. So a lot of times when you're talking about like a lot of times with MapReduce systems, the correctness stuff is less of an issue, and it's more the performance problems that really get people, because they tend to be working on something where you're just dividing it based on separate data.
Shard it,
Shard it, send it out, but then you might have some funny performance problems. So in terms of like how you interact with existing APIs to still deal with performance, I think you can both have tooling that goes on top of there and also like work with from the API level. Sometimes it's not expressive enough.
Okay, thank you. Time for a couple more.
Yeah, hi. In one of your slides, your tool Copper caught a cooperability bug in which there was a missing yield after an unlock.
Yes.
And so I'm wondering if, in general, if not always, it's a yield point. You have a yield point after an unlock. But what I want to get at is it seems it could be struck me as rather cumbersome to instrument programs with yield statements when many programs naturally have points that would be naturally or always yield points.
Yes.
So have you looked into
that's
tools
So that's one thing where inference comes into play. So like you could leverage that information with an inference system. I mentioned like Silver, that's dynamic inference. So there's kind of a statically you can get inference for the whole program, but you might have too many yield points. So there's the trade-off. But you can kind of leverage that information to check whether the inferred points make sense. So like maybe like at a lock point, a lot of times that's an intended yield. One kind of error that people make there's some atomicity violation checkers that look for this pattern where you have two. Let's say I have like acquire M, release M, acquire M, release M, and then this whole thing is wrapped in another lock. So sometimes you actually want two different blocks where you're acquiring and releasing the same lock to be atomic with respect to a bigger lock. So once you have nested locking, then it's not like every point where you release is a point where you want another thread to interfere.
So I presume your yields are just compiler directives, is that right?
Yeah, or in this case, for the analysis, for dynamic analysis. So it's not a compiler directive, but
Well, seeing your talk, one of the recommendations I would make to you actually is you should probably, I recommend strongly urging you give a paper at ASP+.
okay.
In comparison to some of the other conferences you're suggesting as well too, because you actually have the potential. I mean, well, I don't want to make this discussion, for instance, on transactional memory
Yeah.
as an example, but you know, if you start to encounter some of the hardware people, you change some of their thinking and maybe get architectural support, which is the whole purpose of that conference. I have experience on a variety of different hardware architectural types, and you know, they just none of them gain traction. But we can talk about it offline.
Yeah, there's a SEM system that's being developed right now, right, with Intel.
Well, there's that, and there's also, you know,
Could you lean forward with your microphone?
going back, you know, the most notable threaded system that people cite is the Terra MTA, even though it crashed after two generations. But you know, Burton Smith does work for Microsoft. He inputs, as well as other traditional people who work on parallel computing, like Cut working for Intel as well too. You might as well get your 2 cents as well.
Is there a question in there?
Yeah. I asked the question about yield, but it boiled down to a recommendation sheet. Give a paper at another specific conference.
Yeah, let's take those two and then we'll call it off. Go ahead.
Just lean forward.
Okay. A quick question. How do you deal with the pointer aliasing in your static analysis? So does it have an impact, or do you implement a specific pointer analysis?
That static analysis is purely intra-procedural, purely intra-class, and it's like very limited. It doesn't have any very fancy pointer analysis right now. The guarded by one at Google that I was talking about. Yeah.
And do you think that adding a pointer analysis would kind of reduce the weight of false positives, or it's completely independent in that case?
Yeah, I think that's part of the plan is to add that in. There's someone else maintaining it since I left. I think that will help. There's also, so right now it's more like it's the false positives aren't as big a problem as it's just like limited in how you apply it. So it works well for the very simple case where you just have a mutex that you're talking about and some variables, and you just want to say that they're guarded by the mutex. And once it starts getting more complicated, it breaks down in several ways. One solution is to actually have more of like a type system approach. So like, you know, completely, you know, show that everything, but that also is like heavyweight for some developers. So there's like debate over what the most important places to change it are.
I'm a UI guy, and so I kind of wonder about workflow, and you're doing these usability tests, and I kind of have this impression of these old school things where people remember to use some tool, or they, you know, when they have a problem, they see that somebody put in some documentation. How do you think of the trade-off of the effort and energy of getting people to actually use some you know, like structure editors used to force people to get good syntax, or other kinds of tools that actually enforce using those great analysis tools that you were talking about, as opposed to just hoping somebody's going to reason about it and find something and discover some annotation that somebody else put in the program.
So, okay, so this is, so what I've found is that teams have a really different attitude about how into this they are.
Oh, yeah.
So like the static analysis I mentioned, the guarded by syntax. So let me tell you about two teams. So one of the teams, they actually don't have enough annotations in their code to check most of it. So they use it almost exclusively for documentation purposes. Occasionally they add extra annotations to part of their code because they want to run the analysis if they're having a problem, but almost all the time it's just to document, and it's just because it's even shorter than writing a comment is writing an annotation in the syntax. I talked to another team. they wrote independently a tool that analyzes your code, looks for things that look like mutexes, and makes sure that that every variable is actually guarded by a mutex, and that every time that you actually have annotations everywhere that it thinks you should have annotations. So it seems like it's a work style issue with whether people like really are into that and are into more support, so really force them to do it that way, and or really don't want that and will get mad at you if you try to do it.
Great. Okay, well, thank you very much. We're going to have a little break, and people who have questions, one on one, they want to be around for a few minutes.
So do we have soda and cookies out in the hallway? Okay, so that's where we'll have the discussion. It's out there.
Okay.
Okay.
thanks again.